Okay, I've just been given the go-ahead to start. I know it is a wee bit early, but I've been as anxious to get going as I'm sure you've been as anxious for me to actually get going. Thank you all for coming along on a kind of drizzly Saturday afternoon. This is my first time actually doing a live science show in front of an audience outside of a school, because normally I am a primary teacher and I do a lot of science in the school and I do science assemblies, but this is my first time out of the school, so you are my first official science festival audience. I have a range of different things that we're going to look at. Some of these are simple things you can do at home. Some of these are slightly less simple, can still be done at home, but with adult supervision. I'm going to show you how things are done. I'm going to explain how things are done. And also on my banner at the front and on the flyers there's QR codes that will take you to my YouTube channel, where I demonstrate science experiments, mostly using simple household items, because I want people to be able to do science at home without having to spend a fortune, but still get the learning. So you'll find lots of videos on my YouTube and across other social media. So make sure and scan the QR code, head on to YouTube and subscribe. This should hopefully take about an hour. I know people might dive in and out, that is fine. We're going to start at one end and work down to the other end. So if you want to see what's going on down there, you will need to hang about until the end. Going to start off quite simply with my cup of water. I've just put food colouring in it just so people at the back can clearly see that there is water in this cup. And what do you think would happen if I just took this cup and turned it upside down? All the water is going to come out of it. What if I spin it upside down? What do we think then? What do you think? You think it will still come out? You think the water will stay? Well, let's find out. Okay, the water's still staying in, spinning it round in front of me, and I can even get it going right round over my head, and there's no water coming out. Does anyone think they know why the water is not coming out of this cup? What do you think?
Because it's spinning, the water is pushing onto the other end of the cup.
Exactly right. Because it's spinning, the water is trying to get out of the cup, but the force of the spin of the cup is holding the water in place. And to do this, all you need is a plastic cup, some water and some string. I've added a wee bit of tape so my string doesn't come untied and fly off and hit somebody in the face. But when you're doing it at home, do it out in your back garden so you don't break anything in your house. It's a good bit of fun, simple science, a good bit of physics there. You also need to get a good speed going. If you go too slowly, as one of the predictions said, the water will come straight back out of the cup. Now, water has some really interesting properties. One of them is that water molecules will all stick together and hold on to each other. Okay? And you can use this wee bit of information about water to do another cool wee science trick of getting water to go from one cup to another cup along a piece of string. Again, it's just water with food colouring in it so you can see that it's there. This bit of string in the middle has been left in a jug of water. You need to have it soaked in water so that this will work. I need to be very careful not to soak my other experiments. But I should be able to get the water to go from one cup down to the other. And you'll gradually start to see the cup in my left hand filling up with this green water. Can we see that at the back? The water going in to the second cup. Okay, and people up close will be able to see a bit better. There's water actually running down the length of the string, and you can see the string turning green as that green water runs down it. Okay. And that's just because the water molecules are all holding on to each other, and they're holding on to the water that's on the string, so you can transfer the water from one cup to another down the length of a wet piece of string, because all the water is going to hang on together. That will even work at bigger distances. I've done that from way up high in the gym hall to 20 feet to the other side of the gym hall with somebody with a cup down near the floor. So you can do that over a great distance, not just a short distance like that. You need to make sure your string is pulled nice and tight. You need to make sure your string has been soaked first, but you can get the water to travel from one cup, as we saw, down into the other. Another fun thing you can do though with water, because the water molecules all stick together, is you can stop water from coming out of a glass just simply by using a piece of card. So I've got my glass of water here, and this is just normal cardstock that you would get in any craft shop. And if I flip my glass upside down onto the card, holding it down nice and tight, I can stop the water from coming out of the glass. Okay. Now, that will not always hold for a very long time. I went viral when I decided to pass this over my head at a school assembly, at which point the card fell away and I got covered in red food colouring. If you want a good laugh, that's on TikTok. And if we have time when I get to the end of this, I will attempt it again. Okay? I'm not going to attempt it right now because I don't want to carry on from there to here, soaked and covered in food colouring. But I promise, if we have time at the end, I will do that. Who thinks they know why the water is not coming out? I've given you one reason, that water molecules all hold on to each other. But why else might the water not be coming out? What do you think? Because the water's making the card sticky, so it's sticking to it. We are really good with predictions today. That is one other reason. So the water molecules all stick together. They are also sticking onto the card and making the card sticky. And there's one other reason. What do you think, boy with the glasses? It's airtight. And what's actually happening is the air outside is pushing up on that bit of card. So the outside air pressure is pushing that card up, which is helping the water create that sticky seal that we had predicted over here. And all of this works as well because the water molecules are all holding on to each other. This works as well using a thing called surface tension. That's what it's called when water molecules all stick together. Now we have a balloon here, and balloons have surface tension, which is just the stretch over the skin of the balloon. But a balloon doesn't have the same surface tension across the entire part of it. Because you'll always notice when you blow up a balloon at one end, you've got a darker spot here, and at the other end where you tie it, you've got a darker spot there. The balloon is not pulled as tight at these two parts as it is in the middle, which means if this works properly, with a little bit of oil on a sharp bamboo skewer, I should be able to squeeze this into the balloon without popping it. Now I can't go really fast. Right now I can't get it in at all. There we go. So you can get a wooden skewer to go inside your balloon without popping it. Some air will come out because you have created a hole, but who thought that was going to pop when I was putting that in? Because normally that is what would happen with a balloon, is it would pop. And if you're being really daring, you can have a wee competition to see who can get the most bamboo skewers into a balloon before it pops. I've only got 3 here. And we'll see if we can get all 3 in. So again, simple, cheap science that you can do at home with some wooden skewers, some balloons, and some oil. The balloon is starting to get smaller because, as I said, there are holes, there's air coming out, but it's the unpoppable balloon. Okay. It's got 3 bamboo skewers right the way in it. Oh, you can see them poking out just at the end there. I'm not going to try and put them through because then the balloon will pop. Moving down the table, I have a plate of water here and I've put orange food colouring on it. And I'm going to try and get the water from that plate into this glass without picking up the plate or tipping the plate to get it in. Now when this happens, I will try and lift it up carefully to make sure people at the back can see it clearly. But work. So what I'm going to do is take a tea light and I'm just going to set it in the middle of the water. And I'm going to use my lighter to light my tea light. And then I'm just going to put the glass over the top, press it down nice and tightly, and hopefully, if this works, you'll see now that the water is up inside the glass. And there's still just a wee bit left on the plate, but most of the water has gone up inside the glass and the tea light is floating. How do you think I managed to get the water into that glass? Why did the water go into that glass? Even though I didn't touch it, I did nothing to raise it up. Why do we think it went in? What do you think? Okay, that's an interesting prediction. The water would react with the fire. Any other thoughts about why that might have happened? What do you think? Sorry, can you say that a bit louder? Yeah, that's a very good prediction. The fire used up the air that was inside the glass. And there's air pressure all around us. Although you don't feel it, the air around about you is pressing on you all of the time. And when the fire used up the air that was inside the glass, that meant the pressure in the glass was lower. You can come in if you can find a space to stand, you can come in. That meant the pressure inside the glass was lower than the air pressure outside the glass. So all of the air outside was pushing down on that water, and then that gave the water somewhere to go. There was lower pressure in the glass, so the water got forced up into the glass. Going to do another one now. This one should be able to be seen at the back because it does not stay on the table. I've got an empty tea bag. I've cut off the two ends and I've folded the top down at one. I'm just going to stand it on this plate. Again, using my lighter. I'm going to set it on fire and let's see what happens. Oh. Okay, did we see that at the back? Did we see that at the back? Yeah? Will I do another one anyway? While this one's going, let's see if you can work out why this is happening. Oh, it's coming back down on its own. Good. Don't go in my glass. Why do we think that was happening with the tea bag? What do we think was making it fly up into the air? The fire has something to do with it. Boy at the back with the glasses, but you'll need to shout, or Dad might need to shout for you. What? Because of the air? It has something to do with the air and the fire combined. Boy with the mask. Can you say that a bit louder? Because somebody started hitting an instrument over there. The air's pushing up with the fire. We are almost combined all at the right thing. Who's ever seen a hot air balloon flying? Some people. Whether you've seen it in person or on TV or in a picture or whatever. Hot air balloons use this property. When air is warmer, it is lighter than cold air. So warm air rises and cold air comes down to fill in. In a hot air balloon, they have a flame which fills the balloon with warm air. And because that warm air is lighter than the colder air round about it, that is why the hot air balloon lifts up into the air. The same thing is happening here with the tea bag. I've folded over the top end so that we have a bit to trap the air. But when it's on fire, the air inside the tea bag is all warming up and cold air comes in underneath to fill the space of that warm air going up the way. And that's why the tea bag then flies up. That's also why that tea bag came back down on its own before I had to catch it, because then it had used up its air, it had cooled down, so it had no reason to keep flying. There was nothing forcing it up anymore. I like to do that one at Halloween as flying ghosts, but as with all science, you can do it any time of the year. Make sure you use the rectangular tea bags. I've never tried it with a round tea bag, but rectangular tea bags definitely work. And I get people to draw ghost faces on them and things. If you're doing that one at home, children, please make sure adults are doing it with you. I'm not encouraging you to go home and start setting fire to things. Also, please make sure, even if you are doing it with parents, we do it in a safe way. That's why I've got my spatter guard to catch it. I've done it on top of a cooker, so it goes up to the cooker hood. But I don't want to be held responsible for people burning their houses down. So please be nice and careful if you're trying that at home. Does anyone know what is special about today, other than the fact there's a science festival going on? But there's something else going on in the world that is special that's happening today. What do you think? It is Chinese New Year. And that's why I am wearing red today. My next experiment is going to be in honour of Chinese New Year. My wife is Chinese, so we're actually in Edinburgh with her parents this weekend celebrating Chinese New Year, which is why this is a one-day only show. I came back from Edinburgh just to do this, and I'm going back straight after it. So this next one is in honour of Chinese New Year, and it's using my tub of rice and my chopstick. Okay, I've already mostly filled this bottle with rice, so you don't need to sit and wait for me filling the entire thing up. So all you need is a normal empty plastic bottle. I'm not going to promote the brand that it is, but I'm sure we can all tell based on what I've been drinking. But they don't pay me, which is why I'm not promoting them. I'm going to put my chopstick down inside, and I'm just going to carry on and fill the rest of this bottle as high as I can get it with rice. I'm also filling the rest of the table with rice, but that's all right. Gonna give it a nice squash down now that it's filled right to the top. Give it a good squash down and see if I can get a wee bit more rice in here. And now I've got a bottle full of rice that I am holding up by the end of a chopstick. That might be hard for people at the back to see because the chopstick is black, but this entire bottle of rice is hanging from this chopstick. How have I managed to do that? And it's not magic. Oh, you're going with it's magic. What do you think? What? It's sticking to the side. That's a pretty good guess. What were the? It's to do with friction. You get over there, your hand went up and then it went down. Do you want to guess? Yep. What do you think? Sorry? It's all pushed down. So yeah, I have, well, last prediction, right, and then I'll tell you. From what I heard of that, it sounds pretty right to mix in with the others. So the bottle is completely packed full of rice. I've made sure to squeeze out all the wee air pockets in between all the bits of rice, which means all of the rice is holding on to this chopstick. There are thousands, possibly even millions of points of friction of the rice holding onto the chopstick. So when I try and lift that up, all of that friction, all of the rice rubbing against the chopstick is holding it in place. And that's why I'm able to dangle a full bottle of rice just from that bit of chopstick. Now, if I start to shake it about, the rice will move and the chopstick will come out. You can also do a fun thing with friction with some books. If you get a couple of good thick books and start folding them one page, one page, one page, one page, you'll reach a point where you can't pull the two books apart. And you need to flip the pages out. That's a good one to do when you're getting people up to demonstrate, but because I'm filming, that's one that I'm not doing today, but it is one, again, that you can do at home. I want to try and get all the rice out of this because I need this bottle for something else. So that was to do with movement, and you need friction to be able to move. If there was no friction on the ground under my feet right now, I would be sliding about all over the place. That's why you slide when it's icy, because you don't have friction on ice. It's a slippy surface. So we need friction to be able to move, but movement is also a result of reactions. Okay? And for every action, there's an equal and opposite reaction. Can anyone think of anything that shoots up into the air? Anything at all that might shoot up into the air? What do you think? Rockets. Rockets is exactly what I'm going to be looking at for this one. Some people in here will be ages with me and will remember old film canisters. Children, you'll have no idea what an old film canister is probably, because everything's now digital on phones. But it used to be me and mums and dads, if we had a camera, we would take our pictures, we'd have to put it in one of these wee tubs, we'd click the lid on, take it somewhere, and we'd eventually get our photographs back. Now I repurpose these for rockets. So I'm going to fill about half of this with water. Now there's no predicting exactly when this rocket is going to take off. I'm going to put a vitamin C tablet inside, click the lid on, nice and tight, stand it upside down on my plate. I'm going to step, oops, knocked over my kettle. I'm going to step back, and shortly our rocket should take off. And if it doesn't, I've got a second one. This one's always a bit of a waiting game. Watch your head. Thank you. Okay. What caused that rocket to launch? So I had water, I had my film canister, I had a vitamin C tablet. What caused that to propel itself away up into the air? What do you think? Okay, so the water and the vitamin C reacted, which forced the rocket to be pushed up and the water to be pushed down. He's mostly right. There's something in there though about this reaction. What's doing the pushing? What's... It's to do with pressure on the lid, but what's causing this pressure? What happens when you put a vitamin C tablet in water? That's an easier question. What happens when you put a vitamin C tablet in water? It fizzes and you get bubbles. What are bubbles? Word beginning with G. Boy at the back, shout it nice and loud. Yeah, in the blue t-shirt. It's a gas. And this chemical reaction of the vitamin C with the water is producing gas. As the boy said here, that builds up pressure. All of that gas is starting to fill up the inside of the tub. It's got nowhere to go, so it forces a lid down, which shoots the rocket up the way. And that is how actual rockets are launched, not using vitamin C tablets and water, but it's the force of something pushing down the way that forces a rocket to go up the way. Okay, and that's the law of the motion. Every action has an equal and opposite reaction. So the action of the gas pushing down has the opposite reaction of the rocket shooting up into the air. Who would like me to launch another rocket? Okay, we'll do another one, because I am set up with two, if I can find my jug of water. Also, who has a watch on and can tell me what the time is? So I know how long we've been running so far. What? 17 minutes past 1. That's fine, we should be doing all right for time then. Remember at the front, just watch for it coming back down. If you can find a space to stand, you're welcome to come in, or you can stay there if you want. It's up to you. Well, I need to think buy new tubs since I've just lost one. I have plenty of spares, but I was not expecting it to go quite that high and disappear away over there. But that's the fun thing about science. Sometimes you do things and they don't happen the way you expect them to happen, but everything is a learning curve. And these two rockets were set up exactly the same way. So the tubs are exactly the same. The vitamin C's came out the same tub. The water came out the same jug. So then you can do a bit more digging as to why one of them launched higher with a bit more force than the other one. Something we don't have time to do today, but if you're doing it at home, you may have time to do a bit of exploration. You can also test that one with different volumes of water. Put in different amounts of vitamin C. I probably wouldn't use more than one whole tablet at a time because we saw how well that launched, and most people don't have ceilings of that height. So that was to do with motion, with our friction, with our chopstick and our rice, which was to do with how we move, with friction under our feet. We've had our rockets with the law of every action has an equal and opposite reaction. And now we're going to look at something else to do with movement. And this is another law of movement that was brought up or developed by a scientist called Sir Isaac Newton. He developed the law for every action has an equal and opposite reaction. And he also had a law which said objects at rest will stay at rest until they're acted on by an outside force. And what that means is if you are lying completely still in your bed, you're not just suddenly going to move unless something makes you move. It might be you making your muscles move, it might be a sibling rolling you out of the bed, it could be an earthquake. But if nothing happens, you're going to stay completely still. This one, if it works, should hopefully demonstrate that. I always say if it works because sometimes things go wrong that you don't expect to go wrong. I haven't had this one go wrong yet, but we'll see. There's always a first for everything. I have an empty glass, I have a finished toilet roll tube, a plastic plate, and an egg. Just going to balance the egg on top of the toilet roll tube. Now, after a count of 3 from all of you, I'm going to hit the side of this plate and hopefully not break this egg in the process. Okay? So, can I get a countdown from 3? I need a louder countdown than that, okay? Can I get a countdown from 3? 3. And there we go. We've got the egg into the glass. Why did the plate fly that way and the toilet roll tube fly that way, but the egg go that way, go straight down? Why do we think that happened?
Because you only hit the plate and the toilet paper roll and you didn't hit the egg.
Okay, part of that is correct. So that was, I only hit the plate and the toilet roll tube, but didn't hit the egg. The part of that is correct, that is that I only hit the plate. I didn't hit the toilet roll tube. There's a clue in there that I'm saying I didn't hit the toilet roll tube. Okay, so what do we think then made the toilet roll tube go to the side? Okay, so talking about the weight and the plate sliding, so the plate pulled the toilet roll tube because it's lighter and the egg's heavier and it fell down. That is kind of going down the right lines. What do you think? Gravity is what made the egg fall. This plate has a lip on it. Okay, this wouldn't work if I used something that was perfectly flat, but because it's got a wee lip on it, when the plate slides that way, that lip hits the toilet roll tube. And that's what takes the toilet roll tube off to the side, but nothing is hitting the egg because the egg was balanced on top. If you are trying that one at home, one, please don't use a plate that can be easily broken. That's why I'm using cheap plastic plates. And two, don't put the egg balanced up the way inside, because then as the toilet roll tube moves, it will take the egg with it. The egg needs to be lying on its side across the top. Okay? But again, fun one to try at home. Just be careful and don't go breaking your parents' nice glasses or nice plates. Where did I put my drink? So that's us at the end of table 1. Table 2 are ones that are a bit trickier to do at home. Some of these substances are quite harmful, so I'll be putting on my protective glasses and I'm putting on my gloves. Some of them are quite expensive, so these are ones that I don't suggest doing at home. But you can watch and learn the science about them. And all of these are a science called chemistry. We're going to be looking at chemical reactions. This side was mostly all physics. Physical reactions, things moving or making things move. Even with the spinning water cup, that was physics as well, because you've got the spin of the cup holding the water in place. These ones are all going to be reactions between different substances. So, in one of my beakers here, I have 150 millilitres of distilled water. And I'm going to add in the contents of a vitamin C capsule. And just give it a good mix round. Because I want my vitamin C to be nicely dissolved in here. And then into that, I'm going to add 6 millilitres of something called iodine. Now, iodine is a substance which isn't particularly harmful if you get it on you, but it will stain clothes, it will stain skin. It's quite often used for sterilising things during operations and such. I'm going to add my iodine into there. Again, I'm going to give this a good mix round, and you see I've got not an entirely clear liquid, but it's mostly colourless. Okay, so that's my distilled water, my vitamin C tablet, and my iodine. Okay. Into my next beaker, I'm going to add in 140 millilitres of boiling water. I'm going to add in 100 millilitres of 3% hydrogen peroxide. It comes in different strengths, but if you're doing this one, it's 3% hydrogen peroxide that you want. And then I'm also going to add in 2 grams of just simple cornstarch that you would get out the shops. Nothing fancy about the cornstarch. Again, I'm going to give this one a good mix round, just to make sure things are well mixed and dissolved. And again, you see I've got kind of milky white liquid in that one. Now what I'm going to do is add the contents of both of these into a separate jug. Does anyone want to predict what they think might happen when I mix these two together? What do you think? There might be a reaction. What do you think the reaction will show? You think explode? You think it'll bubble? Okay. I'll get them mixed, and then I'll hold the jug up because it shouldn't happen straight away. You'll see we got a complete colour change from two things which were a sort of whitish colour. They've reacted and turned to this sort of black liquid. Okay. The reason for that is the iodide, which is in there. I called it iodine earlier. It's actually iodide, but iodide is made of iodine. But the iodide reacts with the hydrogen peroxide, and it turns it into just its normal iodine substance. Iodine reacts with starch and creates this black colour. So the hydrogen peroxide was reacting with the iodide to make it iodine, and then the iodine was reacting with the cornstarch. And the vitamin C and the distilled water and the boiling water are all in there to speed up this chemical reaction between them. That's called the iodine clock reaction, because you should be able to predict, depending on the mixture of the substances that you've put in, the quantities, should be able to predict when it is going to do that colour turn. Okay. Now that is one sign that there's going to be a chemical reaction, is a colour change. That's a sign that a chemical reaction has taken place. Another sign a chemical reaction has taken place is the bubbling and fizzing that we saw in the rockets, and that's something that we're going to see on this one. Has anyone heard of the elephant toothpaste experiment? A couple of people. Those people with your hands up, keep your hand up if you've seen the elephant toothpaste experiment before. Okay, some people. So to some people, this is going to be completely new. You'll understand why I'm calling it elephant toothpaste when you see it. I've got my 500ml bottle here, my empty 500ml bottle, now that all the rice is out it. And into that, I'm going to add in 250 millilitres of hydrogen peroxide. Now this time I'm using 12% hydrogen peroxide rather than 3%, so it's a much stronger chemical. And hydrogen peroxide can be harmful if you get it on your hands. So again, that's why I've got my gloves on, and when you're working with chemicals, It's better to be safe than sorry, which is why I've also got my eye protection on. So I've put in my 250 mils of hydrogen peroxide. I'm going to put in just some normal fairy liquid. Just a few squirts of that in and mixed around. And I'm going to add some mango coloured food colouring, hopefully to give us an interesting colour when this reaction takes place. Just going to give it a nice mix round, make sure everything is nicely mixed in, the hydrogen peroxide, the dish soap and the food colouring. Then in a separate bowl, I'm going to add an entire packet of yeast, just normal yeast from the shops, nothing fancy about it. Yeast is used in baking, for making cakes, making bread. We've got our whole packet of yeast. And into that, I'm going to add 4 tablespoons of hot water. People at the front may start to smell the yeast in a minute as that gets mixed in with the water. It's got a very strong, distinct smell on it. This does get quite gloopy, but I want to try and get it as mixed in as I possibly can. Oops. Then I'm going to add this in to my bottle. And I'll hold it up so the people at the back can see it. So we've got the whole thing foaming up. Okay. Now when I've done this before, sometimes you get it shooting up and out. This one was a slower reaction. But you're still seeing that reaction going on of the chemicals that have all mixed together. And what is happening there is the hydrogen peroxide is reacting with the yeast. Now yeast is a living substance, and if you put yeast in water it will start to bubble because it has living microorganisms in it. The boiling water is helping the yeast go through that process. The hydrogen peroxide is breaking down the yeast and releasing even more of the gas. That's then mixing with the dish soap. And as we all know from washing the dishes, when you're using soap and hot water, you get bubbles. And that is what's creating this bubbly mixture that's known as elephant toothpaste, because when you get it to shoot up, it does look like toothpaste coming out of a tube. Okay, we've got 2 to go. On the very end here, I have a polystyrene head. Now, I should explain why my polystyrene head looks like I let an artist called Jackson Pollock attack it. People who don't know who Jackson Pollock is, he was an artist that would just drip paint onto a canvas, and wherever the drips fell, that's where it would be. My aim was to inject food colouring into the head, but as I tried to inject it in, it all spurted out, so I decided just to make a nice colourful head. On top of this head, I'm going to pour on some acetone. Who in here is familiar with acetone? A couple of people. I'm surprised more ladies don't have their hands up. because acetone's in your nail polish remover. Just not as strong as this acetone. Okay? What do you think will happen when I pour this acetone onto my polystyrene head? Do you think it's going to melt? Any other predictions? No? Either everyone agrees with melt or people are too afraid to disagree. I will hold this one up for the benefit of the people at the back. I will try and do this as carefully as I can to not spill acetone everywhere. And we should see, as was predicted, this polystyrene head is melting. Oops. And is now collapsed onto the table. Let's get it to melt away a wee bit more. That's why it's better to leave it on the table, so when it collapses it doesn't fall on things. But I wanted to make sure everyone had a good view of that. Okay. So what we've got going on there is a chemical reaction between the acetone and the polystyrene head. 95% of polystyrene is actually just air. And that's why it's so light, even though it's very bulky. Polystyrene, though, is a nightmare for waste disposal because it does take up so much space. Now, covering your polystyrene with acetone is a good way for you to be able to fit it in your bin once you manage to tip it into another container, and it's a good way to stop animals eating it if you put it in a sealed container, but it's not a good way to get rid of acetone completely. Nobody has a good way yet, but it is going to be found in the chemical sciences. So if you are somebody who is interested in science, there are still lots of frontiers, which means there's lots of things for you to explore and learn and discover that could change our world. When you do this, the acetone gets broken down into a sticky substance. It's now covering my gloves completely, which some people do use to stick things together. It can be a good adhesive. But what's happening is the acetone is breaking apart the bonds that hold the bits of polystyrene together. And there's just air at that point. Once the bonds are broken, all you have is air. So the air comes out. That's why there was a sort of bubbling and fizzing going on to it. And the rest of the polystyrene just melts away into that sticky substance. Okay. This is going to be the final one, provided this works all right. There will be a loud noise. So just a warning. I also need fresh gloves because what I'm about to do is use some materials which are very reactive with water. So I wanted to make sure I didn't have any liquid on my hands when I go to do this. What I have in my hands here is a metal called potassium. Now, potassium, sodium and lithium are all metals that are very similar to each other in terms of their properties. If you ever look at a periodic table of elements, you'll see they all come together in a row, in a column, and that's because they all share properties. One of their properties is they are very reactive with water. They're also quite soft metals, so although I said to you it's a metal, just with a twist of my hands there, I've been able to break that into 2 bits. Okay? It's very reactive with water, as I said, so I'm going to put it into this jug. There will be a loud noise. I have the guard here, so hopefully nothing should spray forwards. But I'll drop it in and we'll listen to what happens. Oh, we got no loud noise. It's the first time I've done that and not had a loud noise. People at the front, for the benefits of the people at the back, what did you see happening? Yeah, it went on fire. I have another bit here, so people at the back, if you want to stand up and if people are able to move a bit closer, because this is one I cannot pick up. Can't pick it up while it's fizzing away like that. Let's see if this one produces a loud bang. If not, I don't know why, but I will explain the reaction and why sometimes it does produce a loud bang. No. So what is happening is the metal is reacting with the water, and it's what's called an exothermic reaction. That is a chemical reaction that produces heat. And as the metal is reacting, it is producing hydrogen gas. And when hydrogen gas gets heated up, it usually explodes in a bit of a pop, which is why normally there is a sound to it. But that is why it's going on fire. It's a hydrogen gas being ignited. I'm going to do this again with a wee bit of sodium, which is also a reactive metal similar to potassium. It's also a soft metal, which you can break a bit off of. So this is my very final experiment of this show. So let's see if we get a nice pop to end on. There we go. So, only thing to do now is thank you all for coming. Oh, no, I just remembered I made you a promise, didn't I? Yeah. Okay. Before I almost potentially get covered in water and food colouring, thank you all for coming. I hope you enjoyed it. I know there was a lot to take in there, but I'm trying to show you a nice range of science, from easy to do things at home to more complex things that you normally won't see until you're in a secondary school classroom. I'm going to unclip my microphone because if this goes badly, I don't want it getting ruined. But I did promise. So I'll flip it upside down, pin the water in, and I will try and pass it over my head without it tipping all over me. Oh, there we go. So there's a lot of people online saying that I didn't deliberately drop it in my head. I'll do one more and then I'm not going to risk it again. So again, thank you all for coming. I hope you enjoyed it. I hope you enjoy the rest of your holiday weekend. I'll be rushing back to Edinburgh once I've tidied all this up to enjoy Chinese New Year. If your local Chinese is shut, that's why. So again, thank you. Be sure to scan the QR code, go on YouTube, check me out there. I'm on TikTok, X, Facebook, all under STEM on this time. Thank you very much.